going to go ahead and get started with our next presentation. So neural decoded spatial location selection in augmented reality. Presenting today is Naveen. He is a full-time software engineer at Microsoft working on their Azure cloud platform. He is currently working with Dr. Griffin Millsap through his graduate studies with the Johns Hopkins University Engineering for Professionals program. The research he will be presenting today is the product of work with multiple research mentors that has culminated in the talk you're about to hear.
Hi, folks. I hope you guys can hear me. Hey, everyone. Thanks for introducing me, Blake. And before I get started, I'd like to thank Dr. Griff, Dr. Brock, mentors. Then we have Dr. Wilfan, Dr. Will, with whom I took the course, which kind of sowed the seeds of the whole BCI stuff. And obviously, I have my wife over here to support me through this. So thanks, everyone. Let's get started. Neural decoded spatial location selection in augmented reality. Such a long title. But the idea of the title is it's self-explanatory on what the talk is going to be about. We are going to talk about spatial location selection using neural decoding. So you will use the neural signal, decode them to get your intent, and then select a location in the space. And this whole experiment will take place in an augmented reality environment. Pretty much self-explanatory. Why do we do this? So what's the motivation for having a neural decoded spatial location selection? Why can't you, just tap things or use some other gestures? So I have two examples in front of me to convince you why this is important. First is mind-controlled robot navigation. Essentially, what use case you can imagine this happening is you putting on a headset or whatever BCI device you want, and then think your robot should move left, right, up, down, and navigate the whole robot through a tough environment where you can remotely control that robot. So that's a very good use case why you would need spatial location selection using your neural signal. Another very good example which will motivate this project is neural prosthesis control. Essentially, instead of you move, for folks who cannot move, they can think where their arm should go, up, down, left, right, with multiple degrees of freedom. So using the BCI, if you are able to do spatial location selection, you can then do the decoding of your neural signal to give the target location to your neural prosthesis hand, and it will move accordingly. So I hope I have convinced you enough on why we would need this particular project. So coming back to what we have developed or what we have done, this project is essentially a real-time BCI setup. By real-time, what I mean is you do not have an existing model running, but you rather have the signal going in, and at the real time, it is getting decoded. So it's not some kind of offline analysis that we are trying to do here, but in real time, decoding the signal at the same time as we are navigating through the space here. This particular BCI setup that we are using, and it comes from the black box BCI talk that Dr. Griff gave before, have three major components: the signal acquisition, signal processing, and then the final spatial location selection itself. And I would go into details later down the line. But as he was explaining, we have an open site on BCI board which connects to some electrodes, which will give you the EEG signal. So that's the signal acquisition unit, which will stream the data into a signal processing pipeline, which will have the final decoded class giving out into the spatial location selection in your AR environment. So this is the whole setup that we would be working on. One thing to note here is we would provide a visual stimulation for us to generate the neural response. So essentially, this is an example of exogenous BCI where you have to have an external stimulation before you can get a neural response. The paradigm that we would be using in this particular demonstration is called SSVEP, or Steady State Visually Evoked Potential. The way it works is when you have photons hitting your eyes and then getting processed on your visual cortex. So essentially what happens is if the light is strobing or flickering at a particular frequency, the EEG signal have a majority component of that frequency. So essentially, if you are viewing a light of source 10 hertz, you would see that in your EEG signal, the major peak is of that particular frequency. That kind of shows you that neural response could be driven directly from the photons that are being struck to your eyes. Now, if it happens that your visual field have 4 different light sources, all strobing at different frequencies, so we have seen that the one that you are paying attention to will have the majority component in your EEG signal space. So essentially, if you have 8 hertz, 10 hertz, 12 hertz, and 15 hertz light sources flickering on your visual space, and say you are focusing on the 10 hertz signal, then we would see that in your EEG, the majority component is of 10 hertz and it's harmonic. So we then go ahead and utilize this particular paradigm of BCI to develop our setup for spatial location selection. The other part of the whole process is the environment itself, because you have to provide the stimulus and you have to have an environment in which you can run this experiment. And this happens over the mixed reality or the augmented reality. We have developed this whole framework or this application on WebXR, as Dr. Griff described. WebXR is an application framework similar to Unity, but it is much more scriptable. It's a JavaScript-based framework. What you could do is essentially write down your framework and make it very much platform independent, because you can then connect to this environment through any web browser, obviously which supports the WebXR. In our case, we would be using HoloLens, so Edge is the browser of the choice. So we have our application running on the Raspberry Pi board, which was developed on the WebXR, and it's hosted on an HTTPS port. And through the web browser of my HoloLens, I would connect to that application and would be dropped into the whole augmented reality environment. The next important part of this whole BCI setup is the stimulus presentation. As I said, we need, if we want to say, do spatial location where we present stimulus tied down to the area. So we will say that up, down, left, and right will all have different quads, and each quad will be flickering at different frequency. We need to have those flicker coming through on the screen. Now, the thing with the SSVEP is that the flickering should be very synchronized, and the quad should turn on and off essentially to give you the flicker effect at a very precise interval of the application. What does that mean is it is very much tied down to the refresh rate of the screen on which you are presenting this stimulus. So if you, say, want to present a 20 hertz kind of stimulus, you have to do off, on, and that kind of cutoff has to be done. So there is some consideration that you have to take place so that you get precise SSVEP being presented on a screen along with the correct refresh rate as well. So now let's talk about the whole setup of the BCI that we have. The first unit, as I described, is the signal acquisition unit. The way we do signal acquisition is we use the comb EEG electrode. These electrodes directly sit over the head and is connected to the open BCI site on board, which collects these signal from these electrodes. As I show in the picture, the position of this electrode for this experiment we used is on C3, C4, and PZ. Essentially, the active electrode sits over this area, and the reference electrode goes back on the PZ. Now, you might think, but I just told you SSVEP generates from the visual cortex area, and if we have the active electrodes over our motor cortex, how are we getting that signal? So that's where we must understand that EEG is essentially difference in the signal between two electrodes. So even though our active electrodes are in the motor cortex portion, we still have our reference electrode sitting on the visual cortex portion. So the difference will still have the SSVEP component, and this was good enough for us to get started with the experiment. The reason why we chose to do it like this and not put the whole electrode on the Visual cortex area is just because of the form factor of how the whole thing is built. I just guess it was not meant to sit in this way, and it would require some major hardware engineering to have a more custom ones that could sit just directly over visual cortex. But this is a very close approximation to get those visual signal or the SSVP signal. Now, as I said, this signal from the EEG electrode is then streamed directly into the OpenBCI site-on board. This site-on board essentially does signal amplification and digitization. Once the signal is amplified, it is then sent onto the Raspberry Pi or streamed directly into the Raspberry Pi, which is running our Python code to do the signal processing. So there is a signal processing pipeline listening to this incoming stream of EEG signal and trying to do the whole processing and decoding. So let's talk about that. What does this signal processing pipeline do? Essentially, it does the pre-processing and then feature extraction and finally gives out the decoded class. The thing that we chose for pre-processing is to pass it through a Butterworth filter of cut-on frequency of 1 Hz and cut-off frequency of 40 Hz, a third-order Butterworth filter. The reason to do that is, again, to remove any artifact or any unnecessary signal that might be coming in from our EEG. And this 1 to 40 was enough space for us to accommodate all the harmonics and the signal we were looking for on our SSVP. Once we do the pre-processing of the EEG signal, it then goes into our feature extraction and decoding set. The algorithm that we use for neural decoding here is called canonical correlation analysis. It's a very simple algorithm where we try to do a correlation between our incoming EEG signal and a reference EEG signal. We have sinusoids of reference frequencies for which we are trying to decode, or we know our decoded class should be within 8, 10, 12, or 15 Hertz. So we have generated these reference sinusoids, and we then try to find the correlation between the incoming EEG and these sinusoids. And the one for which we find the maximum correlation, obviously, is the one which we say is our decoded class. So say incoming signal is 8 Hertz, and we have all of these reference EEG signal with all of its harmonic, and we saw that 8 Hertz is the one which is mapping correctly to the EEG signal which is incoming. We say that our incoming SSVP decoded class is essentially 8 Hertz. Now, if that 8 Hertz happens to represent the upside, so our spatial location would be pinning to the upside of the whole space. So this is the whole flow on the application view, so how the user will view it. So essentially, what we will present is in the visual space or in the field of vision, first the user will try to position a reticle. This is the origin position around which you will then try to move or do the spatial location selection. You would go left, right, up, or down. As shown, once you fix your reticle position, then you will see 4 quads around it, and you will fixate your eye on one of these quad. Essentially, if you want to move right, then left, up, or down, whatever position you want. Once you fixate your eyes on that, we'll start to flicker these quads, and then simultaneously the BCI will be doing the decoding. So after the flicker is over, the decoded class will be rendered out into your WebXR. In our case, we were fixating on the right, and as you can see, we finally put a sunflower over there, which is just our way of saying that, hey, you moved or you targeted the right location. And then the experiment continues. So now I'm going to play a demo for you, which we recorded with our test subject, Dr. Griff. The right side represent, well, the first person view, and the left side is the actual experiment run. Hopefully, you can see what's going on here. Okay, so what did we see here? We first saw there was a panel out there which was showing the recorded EEG signal, but more importantly, our subject tried to focus on a particular location. So first he fixed the reticle, and then he saw the quads around it, and he wanted, hey, let's go down from there. So he fixated on the down quad, and after the whole experiment run, we were able to pinpoint or select that location. After that, again, say we want to continuously move across the space. So we again showed like the 4 quads around the final decoded location, and then so on and so forth. So essentially what this demo shows you is you can continuously move through your space without ever thinking about having some kind of training or down period just because it is real time. I really want to focus the difference here that you are not fixed to a particular scene. As you saw, Dr. Griff was moving in the experiment run itself. So you can actually map out the whole location, move out through the whole location, obviously on your virtual reality or augmented reality headset, and then map out everything and seamlessly move through your whole environment, trying to do this spatial location selection at different points without being fixated at a particular geography. Well, that was my talk. I hope you liked it, and if I'm here for any questions that's out there. Thank you.
Thank you, Naveen. We have about 13 minutes until our next talk, so we have plenty of time for questions. Please step up to the mic so that we hear you.
Thank you for the talk. I was wondering how you were, there are usually artifacts of various muscle movements such as blinking and just your head movements, and then also the just motion artifact in terms of the participant moving through the space themselves. How did you deal with that?
Well, there is no good answer here. So we tried to, the only pre-processing that I tried to do is just to use a Butterworth filter. And that's pretty much because we know that our frequency range is limited between what we need, and that kind of helped us remove any of those muscle movement artifact in the whole experiment. As for the movement, it is not that much shown if you are doing an SSVP kind of EEG, or that's at least what I saw on the experiment. So that's pretty much a very simple answer for this.
Okay, thanks.
Well,
Hey, so I was just curious, how did you get the immersive AR thing to work on the Microsoft Edge browser on the HoloLens?
well, I guess the folks who are laughing, they know what happened for us. So apparently, Microsoft HoloLens updated their firmware version and updated the Edge version, and that has broken the AR. So if you guys want to use WebXR right now, please do not upgrade your HoloLens, or just stop the update, or never connect it to internet. That was kind of a big deal for us because we went through like many of the HoloLenses yesterday trying to find the one that is not updated. And finally we found one, so we are still up for the demo today, rendering 3 others useless. So thanks for bringing it up. Yeah, fun times, I guess. Any other questions? All right. Thank you.
Thank you very much.